I've hidden myself in a cave here somewhere. It could be my house, could be somewhere out in the state. I don't know, right? I don't want to give away my location because I don't think the College Board wants me to give this lesson, okay? Come here. It's the way to build Taylor polynomials the easy way. They don't want you to know this, okay? But I want you to know it. So don't say a word, okay? I'm going to give y'all the inside track. Are you ready? Okay, here we go. What do we need here? We need to know what the Maclaurin polynomials for the four standard sine x, cosine x, e to the x, and 1 over 1 minus x. Sine and cosine both alternate. Sine is all of the odd powers and factorials. Cosine is all of the even powers and factorials. Because sine is odd and cosine is even, right? Based on the shapes of their graphs. E to the x was all positive, all powers, all factorials. And then 1 over 1 minus x was our geometric series, right? That has a first term of 1 and a common ratio of x. So we have that. So you need to know those four. I'll show those to you later, just in case, if you want to write those down, if you don't have them already. But then another thing we got to do is be able to use the distributive property. And you're in calculus, so I think you know how to use the distributive property. And then you need to be able to substitute. And I think you know how to do that too. So if you can do all those things, come on, let's do it. All right, we're going to make a Maclaurin polynomial for sine of x squared. Now, before you go the easy route, let's think about how we would build any Maclaurin or Taylor polynomial, right? Based on the general form of a Taylor polynomial. It's the nth derivative at the center divided by n factorial. That's the coefficient. And then we multiply that by x minus c raised to the n. And we do that from n equals 0 and on and on and on we go. Okay, so in my last video, I showed you how to use a table of values to stay organized. So here we go. When n is 0, of course, that's the original function, sine of x squared, sub in 0 at 0, so that term is not there, that the coefficient is 0. So the derivative of sine x squared, that's a little chain rule. So that's cosine of x squared times 2x, got it. Plug in 0, we get 0 again, okay. Nothing's happening so far. Let's take the derivative again, let's keep going. So that's product rule now. So the first times the derivative of the second plus the second times derivative of the first. So 2x times negative sine x squared times the derivative. So times 2x plus the second cosine of x squared times the derivative. So times 2. Simplify all that. We get, oh, yeah, there it is. Okay, things are looking fun, right? All right, plug in 0. Okay, you get 2. Yes, something not 0. Divide that by 2 factorial. The coefficient of x squared is 1. Okay, we got a term. Yes. Let's keep taking derivatives. All right, so the derivative of negative 4s, that's product rule there, and then we're going to have to chain rule all over the place. Well, you know what? Here it is. Here it is right there. We'll plug in 0. And you get 0. So all that derivative for nothing. The term doesn't... Okay, you ready to take another derivative? Here we go. No, not doing it. Sorry. So far, with 3 derivatives, we have a grand total of 1 term. 1. And we don't even know if this next one is going to result in anything. I'm not optimistic. In fact, it's going to take until n equals 6 in order to get something that's not 0. Yeah, you're bailing, just like me. You're not taking the derivative of that thing. No way, unless you're just a glutton for punishment. And then after that, it's going to take until n equals 10. and then n equals 14. So like every 4 derivatives, we're going to get something that's not 0. And I don't think we're going to do that because it's going to take some super tedious chain ruling, product ruling, just mind-boggling. Don't mess up at all. It's going to take 14 derivatives just to get 4 terms. Yuck, right? So there has to be an easier way. There has to be an easier way. Well, guess what? You're here on this video. Collegeboard doesn't want you to know this, okay? So, shh. Here to tell you how to do it the easy way, okay? So, all right, you're here to see how to do it easy. So let's think about what we've got to be able to do here operationally. Algebraically, there's composition of functions. We can do distribution, the distributed property, and then just simple collecting like terms. With calculus, we can integrate, right? We can integrate pretty simply. We know some of the rules, but like power rule is all I'm talking. We're talking about polynomials here, right? So if we can integrate a polynomial, it's pretty easy to do that. And then taking derivatives of a polynomial is also very easy. So those are the key operations we're going to be considering here over the next few examples. So let's get started. Let's do sine x squared again. All right, so let's look at sine x squared and let's do it for real this time. Let's realize that sine of x squared ain't nothing but a composition of functions, right? It's x squared subbed into sine x. Well, if we agree that sine x is the same as that Maclaurin polynomial we came up with, right? Here it is. Sine x is all of the odd powers, right? So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. If we're saying that that is sine x, and it is for all x, then we should just be able to sub in x squared, right? So composition of functions here. Sub in x squared, see that done in red. So I'm just replacing the x with an x squared and then simplifying, right? There's like zero calculus in that, right? So now we know sine of x squared is x squared minus x to the 6 over 3 factorial, just simple exponent cleanup there. Now, so backtrack a little bit. How did I know after the first 3 or 4 derivatives that I took there, how did I know it was going to take until n equals 6 to get my next non-zero derivative? Right, recall, like in the last video, I talk about how to identify the derivative information. And the nth derivative information is always attached to the nth power term. So you can see how we have an x squared term. So there is a second derivative value that exists. It's non-zero. And the next power we get is x to the 6th, which means that the next non-zero derivative is the 6th derivative, and then after that, the 10th derivative, the 14th derivative, all the other derivatives in between are all 0. That's why it would have taken 13 really, because we don't, not counting the first one, would have taken 14 rows of that table to get 4 terms. That would have been not fun. Okay. So here we can actually find the value of the 14th derivative as 0. Just a little rewind here. Now, based on the term, the x to the 14th term, right, we know by the general formula that the 14th derivative is hiding in front of x to the 14th, right? It would have been by the general term, the 14th derivative at 0 divided by 14 factorial. It just so happens that coefficient is -1 over 7 factorial. So we match the coefficients. We say, well, that general coefficient is equal to that specific in the pattern. Easy algebra later. We know that the 14th derivative of sine of x squared evaluated at 0 is this critter right here, -14 factorial over 7 factorial. I'm not multiplying that out, but that's what it is, okay? Now, again, you can you can go back and check those. You can check that answer by taking 14 derivatives, and you won't. Just take my word for it, okay? All right. So here are those series. Just in case you wanted to see them again, you want to jot these down in your personal notes. You want to like a tattoo of these things on your arm. I would not recommend it, but hey, it's your decision. All right, as long as you're over 18 or whatever the legal tattoo age is, these series are going to be important to know, right? You have to know these series because we're going to base everything else in this lesson on these 4 series to just plain know. What else do you have to do? What else do you have to know other than these 4 series? Well, the operations, distribution, substitution, all those other things, which I'll show you some examples of. And you also need to subscribe to my channel. You also need to hit that notification bell so you don't miss out on any awesome calculus content. Thank you. Let's check out another one. Let's check out the polynomial for x e to the x squared. Okay, x times e to the x squared. We can see that x e to the x squared is going to be a beast to do by the table. It's already product rule. You see chain rules thrown in there because we're raised to the x squared. Not going to be fun. What we do need to recognize is that e to the x squared is a composition of functions, and then that multiply by x is just going to be we're just multiplying the whole critter by x. So a mixture of composition and distribution. So with the order of operations in mind, first thing we would do is we would want to do composition first. So e to the x, right? That's the glorious e to the x. Man, what a beautiful polynomial that is. And we're going to sub in x squared in place of each x, right? We're not just upping all of the powers by 2, right? We're replacing. This is a composition of functions. We're plugging in, substituting in x squared in place of x. So x squared, squared, x squared, cubed, x squared to the 4th, and then a little exponent cleanup gets us there. So there's the polynomial for e to the x squared. And then we're just going to multiply the whole kit and caboodle by x. So x times e to the x squared is just x times that polynomial we came up with for e to the x squared. Well, that is just going to increase all of the exponents by 1. So now I know the polynomial for e to the x squared, and I didn't have to take a single derivative. Pretty nice, huh? That's why Collegeboard doesn't want you to know this. They don't want you to do it the easy way. They want you to do it the hard way, right? They want you to spend $100 on this kind of information. No, I'm giving it to you for free on YouTube. All I'm asking for is like a like below. All I'm asking for is a subscription. All I'm asking you to do is hit the that's it. Notification bell. Man, that's all you got to do. I'm not charging you any money. This is amazing kind of stuff. It should be free. All right. And then the general pattern, salute, would be, right, this is x raised to a increasing by 2, starting at 1, so that would be x to the 2n plus 1, and then we're divided by just the same factorial, so just over n factorial, just in case you were wondering. I don't know if you were, but that would be the general pattern for e to x, e to the x squared. All right, let's keep this ball rolling. Here we go. Maclaurin polynomial for x squared over 1 plus x squared. Now that one is reminiscent of the geometric series. Okay, so that one is the function 1 over 1 minus x just manipulated, right? So you can recognize that negative x squared is getting input in place of x, and then multiply the whole thing by x squared. So that's one way to think about it. If we think about the operations I listed earlier, all the algebra and calculus techniques, the operations we were going to use. So here we go. Start with the base model, 1 over 1 minus x. There it is, the geometric series, 1 plus x and x squared and x cubed and so on. We're going to sub in negative x squared in place of all those x's. Here we go. So 1 over 1 plus x squared, you see it there, it was 1 over 1 minus negative x squared. Poppy, pop, 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 get them all in there in place of x, and then clean up. All right, so 1 over 1 plus x squared, which again is a geometric series. First term is 1. Common ratio is negative x squared. That's maybe another way to see this thing. And then we're going to distribute x squared to the whole kit and caboodle. So you multiply by x squared to the function. It's the same as multiplying x squared to the polynomial. And that is just going to bump all of the powers up by 2. So here we go, x squared over 1 plus x squared. You see it there, there's the polynomial. And not a single derivative was necessary. Oh, man, that was easy. Yeah, and again, that's just a geometric series whose first term is x squared and whose common ratio is negative x squared. And you can see how that works. X squared, well, then negative x to the fourth, and positive x squared. And you can think about it that way too. You don't have to do the composition and distribution if you think about it as a geometric series. Okay, now, the fun one. Oh man, get ready. Just buckle up, because the next one is going to be tough. All right, fourth degree Maclaurin polynomial for e to the x times sine x. Yeah. All right, so we're not going to take any derivatives, not going to do it, wouldn't be prudent, not at this juncture. What we want to do is we just want to apply some simple algebraic operations like multiplication, distributive property, kind of get that in the mix here. So this one's going to blow your mind here. You might want to download the notes for this one and check it out. We're going to distribute infinitely. Yes, won't that be fun? Check it out. E to the x times sine x. Here it is. All I'm doing is replacing e to the x with its Maclaurin polynomial. There it is in red. And then sine x, I'm just replacing sine x with its Maclaurin polynomial, the one with all the odd alternators. All right. So there you go. I gotta foil this thing out. I gotta foil, and I never get to L. So think about distributive property. It's like everything in the red has to get multiplied by everything in the blue. So I'm just going to take each piece of the red and multiply it by all of the blue. So here we go. Yikes. Don't be scared. It's just multiplication. All right, so 1 times everything. X times everything in the blue. X squared over 2 times everything. X cubed over 3 factorial times everything. Okay. Now, it wants a fourth degree, right? Let's backtrack. Fourth degree. Think about fourth degree. We don't really care about anything above a fourth degree. So if you see something here, if I went x to the fourth over 4 factorial and multiplied by everything in the blue, I'd already be bigger than x to the fourth. So I'm not going to worry about anything bigger than what I've got. So it's just distributing here, just multiplying by 1. That was easy. I could do that pretty simple. Just multiplying by x. That was easy. Multiplying by this. Okay, there we go. That's all there. You can pause the video and check it out if you so desire. And then I get to collect like terms. So collecting the like terms that are fourth degree and less, there they are in red. Well, I'm just going to combine the like terms there and get x plus x squared minus x cubed over 3. The fourth degree terms end up being 0. There is no fourth degree term. Now, lest we forget what we're trying to do, we're trying to make a polynomial function vacuum sealed onto the function e to the x sine x. And just in case you were wondering, here it is, right? The blue one is e to the x sine x. And the cubic, x plus x squared plus a third of x cubed, look at that. Look how close all that is, centered at 0. Look at that, just hugging nice and tight, close to the function. Well, I went ahead and found the next term the fifth degree term just for kicks. I did it you can do it on your own. You can confirm that it's negative 1 over 30 times x to the fifth if you just go a little bit further. Well, you graph that sucker, and that's the green one there. Look at the green one. It's just a little bit closer for a little bit longer, just lingering on that hug of e to the x sine x for just a little too long, like a creepy function. Okay, there you go. Just to get a visual, just so you see the visual. All right, so far so good. We're rocking. Now hold up. Bogus thinking alert. Now the reason composition works is that the final result was a polynomial centered at 0. So if you want a Maclaurin polynomial and the final result is centered at is a Maclaurin polynomial, then it worked. But composition doesn't always work. Okay? You think it should, because why doesn't composition always work? I mean, you can always sub in what you want. So case in point, sine of 2x plus pi over 4. I believe that was even a homework assignment on the last thing that I gave to my classes. So if you just use the idea here of composition and you want to build a Maclaurin polynomial for sine of 2x plus pi over 4, well, you could just start with the standard sine x model, x minus x cubed over 3 factorial, yada, 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 and then just sub in the critter 2x plus pi over 4. Well, there you go. Why can't... I'm done. Not so fast, right? That is not centered at 0. We wanted Maclaurin. Did we get Maclaurin? Nope. That means, sorry, Charlie, and everyone else who isn't named Charlie, you can't do composition on a thing like that, okay? The center is actually negative pi over 8, and that ain't working for a Maclaurin polynomial. So this time, to get a true Maclaurin polynomial for that function, you would have to rely on the table. You'd have to rely on the general form of a Taylor polynomial, which is kind of a bummer. It doesn't always work, but you know, that's just how the cookie crumbles. Okay, so let's use some calculus now. We've seen composition, we've seen distribution, simple distributing just a single term through a big group, and we've even seen infinite distribution. Holy cow! Let's see how we can use some calculus now. So derivatives and integrals. So e to the x. Y'all remember e to the x? Oh, wasn't it just adorable? 1 plus x squared over 2 factorial. You know the rest. Well, you know what? Let's take the derivative, shall we? The derivative of e to the x equal to the derivative of this other side. Pause the video, do it yourself. Okay, it's amazing. The derivatives end up being exactly the same. It's the original, right? The derivative of e to the x is itself. This is like the only function that does that. Well, guess what? There's another function that does that, and it's the infinitely long polynomial that matches. Oh my goodness. All right, my computer's gonna die. Hold on. Hold your horses. I have to recharge. There. Done. All right, now let's integrate just for kicks. Let's integrate both sides. All right, integral of e to the x dx is kind of funny, but the integral of this polynomial, let's check it out. Right, the integral of e to the x is e to the x. The integral of 1 is x, then x squared over 2, then x cubed over 3 times 2 factorial, then x to the 4th over 4 times 3 factorial. You see where this is going. Plus a constant. Well, guess what? If e to the 0 is 1, and you plug 0, 1 into that equation to figure out what the value of c is, you get that c is 1. And that means if you integrate e to the x as an infinite polynomial, you get the same polynomial back. What? Yeah, right. So freaking cool.
Actually, that is the coolest thing I've ever seen.
Oh yeah, and by the way, the derivative of sine x Yeah, it's cosine x. Little spoiler alert there. Well, if you take the sine x polynomial right here under that yellow big bar there, the derivative of x is 1. The derivative of x cubed over 3 is 3x squared over 3 factorial. Then the derivative of x to the 5th, that's 5x to the 4th. And then you simplify. You get this critter over here. That look familiar? Oh yeah, that's this cosine x Maclaurin polynomial. Wicked, wicked, wicked. All right, last one. This video is lengthy, but oh my gosh, it's so amazing. It's going to make this so easy for you. But again, mum's the word. Don't tell the College Board. All right, arc10. How do we come up with arc10? Well, you could use the table. All right, so let's do it. The zeroth derivative of arc10 is arc10. Easy. The derivative is 1 over 1 plus x squared. The derivative of that is, okay. This is starting to look ugly now. You could use quotient rule. You could use, this is 1 plus x squared to the negative 1. But then it's like, oh my gosh, then I'm on to some kind of power rule after that, or product and power and chain, and things are just going to get ugly. So here's what I can do. Now, 1 over x squared, right? We know that the integral of 1 over x squared is arc10x. And I bet you know how to make the function 1 over 1 plus x squared pretty easily. Can't you? Can't you? It's just a geometric series whose first term is 1, whose common ratio is negative x squared. We did it a couple examples ago. Let's go back. Right? We did it already. 1 over 1 plus x squared was this critter right here. And guess what we're going to do? That's right. We're going to swap it out for the function 1 over 1 plus x squared. So that's what we're going to integrate and set equal to arctan. Well, integrate term by term ain't nothing but a thing. It's just power rule. So that's x cubed over 3, x to the 5th over 5, negative x to the 7th over 7, plus some mystery constant. By the way, arctan of 0 is 0. So when you plug in 0, 0, you get that c is 0. And what's arctan? That's right. It's the polynomial you see there. Wicked. Wicked. Guys, this is some awesome stuff here that you guys just learned a secret cheat code for building Maclaurin polynomials using the existing 4 base models that we know. Now we can use algebra operations like composition, distribution, and polynomial addition to just create some new polynomials based on the 4 you see here. You need to know those. All right. I can also build some polynomials and do derivatives and integrals because it's easy to do derivatives and integrals of polynomials. Not always easy to integrate like weird functions, but it's always easy to integrate and take derivatives of polynomials. So that's going to make life so much nicer. Now, that does it for this lesson. Next time we're going to talk about something called an interval of convergence. Get ready for that. It's going to be a good time. We're going to bring back the ratio test. All right, so we've made it to the end. Thanks for hanging in there with me. I really appreciate it. Can't wait to see people. It's 2021. We're going back to school in a couple weeks. I'm still going to be making videos for you guys because I love doing this. I just want you to have this forever. And then when I come back and I'm 75 years old and I see myself as a younger man, I'll be like, oh yeah, oh man, I love Taylor polynomials. Oh man, hope you do too. Okay, peace everybody. See you next time.